Hello everybody, Mr. Hasty here. Today we're going to start Chapter 8 and Section 8.1's on L'Hopital's rule. So a little bit of background. If you remember, at the beginning of the year we discussed the concept of limits. We then used limits to define something called a derivative. Spent most of first semester talking about derivatives. Most of second semester we've been talking about antiderivatives and their relationship to the integral. So we're going to come full circle here, and we're again going to talk about limits. Now, we used limits to find derivatives early on in our work. What L'Hopital's rule is going to do is allow us to use derivatives to find limits, kind of in a reverse order. So there are some things called indeterminate forms. We are all familiar with quite a few rules in mathematics, things that we take for granted, such as the fact that 0 divided by anything, quote unquote, is 0, or that infinity plus 5 is just infinity. Well, there's a number of indeterminate forms, things that when they come up, we don't know if they're 0, undefined, infinity, or 6. In fact, we're going to learn that they could be any one of those. So our indeterminate forms we're going to look at are going to be 0 divided by 0. Now, two rules of thought kind of pervade here, actually three. Usually if we have 0 divided by anything, it's 0. Usually if there's a 0 on bottom, it's undefined. And usually anything divided by itself is 1. So all those are possibilities and more when we have 0 divided by 0. The second indeterminate form is infinity divided by infinity. And we can mess around with the positive and negative infinities as well there, but basically we learned that anything divided by infinity, a constant divided by infinity, is supposed to be pretty close to 0, and infinity divided by a constant would be infinity. But in the case where we have infinity divided by infinity, it's problematic. The next one is 0 times infinity, because we learned that infinity times a constant is usually infinity, and 0 times any constant is 0, but because infinity is not a constant, it's not a number, this is indeterminate. We're also going to have infinity minus infinity, which could be 0, it could be infinity, it could be 2. And I'm saying 2 is like any random number. The reason why these are indeterminate is because we do not know what these will end up equaling. The last three we're going to look at are the exponential forms. If we have 0 to the 0 power, if we have 1 to the infinitieth power, or if we have infinity to the 0 power. Those are our indeterminate forms. And today we're primarily going to focus on the first two, 0 divided by 0, infinity divided by infinity. Next video we'll do these two. And on the last one we'll do these three, which all have a similar operating procedure. So what does L'Hopital's rule say? So there are some conditions. So the formula we're going to end up using is that the limit as x goes to a of f of x over g of x is going to equal the limit as x goes to a of f prime of x over g prime of x. Now this formula is not true in all cases. There are some conditions that need to be met. So we have to note that f of a has to be equal to g of a has to be equal to 0. So basically this is how we get our 0 over 0. If you were to plug a in for x in both the top and bottom of the initial fraction, we would get 0 over 0. We also need to be guaranteed that f prime of a and g prime of a exists. Usually if we have learned to do a derivative before, we know that those derivatives do exist. And finally, of course, because we're dealing with a fraction, g prime of a cannot equal 0. If those conditions are met, then this formula holds true. So we're going to now step into applying this formula to a couple problems. So we're going to start off with examples of the form 0 over 0, which is the base case, the case we define for L'Hopital's rule. So example number 1, let's say we have the limit as x goes to 0 of sine x over 5x plus 2x squared. Now, when we first learned limits, go-to step number 1 was always to try to plug in the limit value for our x's. And if we do that, we get sine of 0, which is 0, over 5 times 0 plus 2 times 0 squared, which is also 0. You need to make sure that the form is indeterminate before you move forward. Otherwise, you could end up doing L'Hopital's rule in a situation which it does not apply. So always check to make sure that when you plug them in, you do get 0 over 0 or one of our other indeterminate forms. So we're going to apply L'Hopital's rule, and I typically indicate that by putting a little LH for L'Hopital over the equal sign to imply how I made that step. So the limit as x goes to 0 of, now this is not a quotient rule. It's literally just the derivative of the top and just the derivative of the bottom. So the derivative of sine is cosine. Now if your brain went negative cosine, you're still on antiderivatives and you're going to have to correct your thinking. On the bottom, the derivative is going to be 5 plus 4x. And we simply attempt to plug in 0 again. Well, now we won't get 0 over 0. We're going to get cosine of 0 over 5 plus 4 times 0. And we work that out numerically. And cosine of 0 is 1, so this is going to be 1/5. All right, so example 2 here. One of the things that a lot of examples, in fact, most of the examples in our book do, is they use x going to 0, but it could be any value. So let's say we have the limit as x goes to 4. Then we're going to have, well, let's define our initial problem. The square root of 5 minus x outside the square root minus 1 all over x minus 4. So if we tried to plug in 4 here, we would get 0 in the denominator. That's pretty clear. And on the top we get 5 minus 4, which is 1. Square root's 1 minus 1 is 0. So this is a 0 over 0 case. We can apply L'Hopital's rule. Now, what if we couldn't apply L'Hopital's rule? We have to actually go back and use some of the techniques we learned way back in chapter 2. So we'll take the derivative of the top and the bottom. We got to be careful with this derivative of the top, though. The derivative of the bottom is just going to be 1. That minus 4 is going to 0 out, and the derivative of x is just 1. But on the top, we have to apply a chain rule. So we can think of the square root of 5 minus x as 5 minus x to the 1/2, which means its derivative is going to be 1/2 times that quantity to the negative 1/2. Now we have to multiply by the derivative of the inside. The derivative of the inside is going to be negative 1. So on the top, I'm going to get negative 1/2 root, quantity 5 minus x to the negative 1/2. And now we're going to plug in our value. So if we do that, we're going to get negative 1/2 times the quantity 5 minus 4 to the negative 1/2. 5 minus 4 is 1. 1 to the negative 1/2, that'd be like the square root on the bottom. It's end up going to be 1 as well. Times negative 1/2 will be negative 1/2 as our final value. All right, let's look at infinity over infinity examples. Okay. So how could this come out as infinity over infinity if the original definition was 0 over 0? So let's quickly talk about how that applies. So we have to remember a couple odd facts from way back. So infinity we've talked about this in terms of limits can be thought of as 1 over 0. If you get a 1 over 0 in a limit, that means infinity. Why? When you get really, really, really close to 0, what it means is you're getting a very, very, very small number. 1 divided by a very, very, very small number is a very, very large number, and that we call that infinity. So using the rules we understand for fraction arithmetic, we get 1 over 0 times 0 over 1, which is 0 over 0. So they are equivalent in a way, and that allows us to apply the rule to the case of infinity over infinity. So example 3 here, we're going to start off with a limit as the variable goes towards infinity. Say we have ln x over, say, x squared plus 2x. So if we plug infinity into the top, if you remember what the natural log curve looked like, it looks as follows. It continues on infinitely upward. So we would get infinity. As we plug in x, we would get a y of infinity. And on the bottom, we're clearly going to get infinity because we're going to square infinity plus 2 infinities. So this allows us to apply L'Hopital's rule. The derivative of natural log of x is 1 over x. And the derivative of x squared plus 2x is 2x plus 2. Now, if we try to plug this in right here, it's going to come out a little bit odd, but let's simplify it first. We're going to move that 1 over x onto the bottom and distribute it in, so we'll get 2x squared plus 2x. So the bottom is going to be infinity, but the top is going to be 1. We dealt with that a long time ago. When that happens, we have 1 over infinity. That's going to be 0 as an answer. So this whole function is going to tend towards 0. So let's do a one-sided limit real quick. Let's do the limit as x approaches pi over 2 from the right side of secant x over 1 plus tangent x. So we have to remember real quick, pi over 2, secant is 1 over cosine. Cosine of pi over 2 is 0, so the top is 1 over 0, which is infinity. And the tangent of pi over 2 is sine over cosine, so 1 over 0, which is infinity, plus 1 would still be infinity. So we can apply the rule here. So our derivative of secant is secant x tangent x. And the derivative of 1 plus tangent x, the 1 will 0 and the tangent x will go to secant squared x. And now we can do some cancellations. We can cancel out a secant top and bottom. And when we do that, we are going to get tangent x over secant x. And we're going to have to, if we try to plug in pi over 2 here, we get some similar issues, but we can keep simplifying. Secant is sine over cosine. And this is 1 over cosine. Using our rules that dividing by a fraction is the same as multiplying by the reciprocal, we can cancel out the cosines. We get the limit as x goes to pi over 2 from the right of sine x. If you can plug pi over 2 into sine x, you're just going to get a value of 1. So the infinity over infinity case is just a specific variation on the 0 over 0 case. That won't be true of the other indeterminate forms we do. So lastly, we're going to go over a couple specific cases. So the first one is that you can apply the rule multiple times. So for instance, we're going to do one that we actually learned some tricks for back in chapter 2, but we're going to see it in a different way. If we do the limit as x goes to infinity of 5x cubed minus 3x plus 7 over 2x cubed plus 4x squared minus 1. You might remember there was a trick to finding this limit that we learned back in chapter 2, but with L'Hopital's rule, we don't need to remember the trick. We can just keep applying it. If I plug infinities into all these, now you might be like, well, I have an infinity minus infinity, but if one of the terms is larger, that term is going to decide whether it's positive or negative. And so this is going to be positive infinity over positive infinity. So I'm going to apply L'Hopital's rule. And you get the limit as x goes to infinity of 15x squared minus 3 over 6x squared plus 8x. If I plug infinity again, I'll still get infinity over infinity. So we're going to apply L'Hopital's rule a second time. And I will get the limit as x goes to infinity of 30x over 12x plus 8. Still would get infinity over infinity. Apply it yet again. We'll get 30 over 12. So it doesn't have any x's anymore. We can just reduce the fraction 30 over 12, which comes out to be 5 over 2. And if you remember the trick is if you take the lead coefficients and make a fraction, that's going to be your limit. That's kind of where that trick comes from. So one of the things that's important to note is limits can still come out infinite, meaning that the limit could tend towards infinity. What is a limit, especially a limit that goes towards infinity? If we remember how asymptotes work, this would be the limit as x goes towards infinity of whatever function this is would equal 0. But if we have a function that is just going off into the sky there, then that one would go towards infinity. And if you went downwards, you go towards negative infinity. So let's look at an example of that. If we have limit as x goes towards infinity of x minus 2 over the natural log of x. If I plug infinity into the top, I get infinity minus 2, which is still infinity. If I plug infinity into the bottom, we talked about that earlier, natural log of infinity is infinity. So we can go ahead and apply L'Hopital's rule here. Limit as x goes towards infinity of the top would be 1, and the bottom would be 1 over x, the derivative of natural log. So simplifying that, we get the limit as x goes to infinity of 1 times x over 1, which is just x. So the limit as x goes to infinity of x is just infinity. All right, Monday we'll keep tackling our slog through the various indeterminate forms. Hope to see you there.